What?
Is that the same in Russia as well and China? I mean, or do they have a more continuity there?
I don't know. It's, I know how the Japanese program used to work from being an insider.
Yeah, I can hear you.
You betcha. Oh, back to waves.
Okay. It's shared.
Ivan, you might want to go back one slide just to catch people up, if you can. Here we are. So once again, the guys upstairs are doing stuff.
Yep.
In other news, some more of the human genome got sequenced.
Yeah, I understand that at this point we can almost say that the entire genome has been done.
An entire genome. We still haven't got it all. The Y chromosome is apparently a tricky thing to sequence. But then beyond that, of course, there's a difference between a human genome and the human genomes of everybody everywhere, which is, of course, a much larger collection.
So, Abby, I'm surprised by that. I thought it had already been sequenced, like long ago.
That's what we were told. Yes. No, back, I guess it was in 2000, I think it was, we had supposedly sequenced the human genome, but it turned out that although they kind of had it complete end to end, there were gaps in between where for some reason we didn't have the technology to figure out every last detail. And recently a whole bunch more has been published. But there's some tricky business with the parts of the genome that are only on one chromosome or another, because you can't look at a complete human being and get that. So we're having a little bit of trouble apparently with parts of the Y chromosome. And then we should at least have a complete, when that happens, we should have a complete sequence for at least one human. But there are lots of people. And we're going to have slight differences. So there's still a lot more that we can find out about this, but also just closing the gaps even on one is an important thing to do.
But when they sequence a genome, and let's say they're sequencing a genome for, like, I'm aware that when they made predictions about how long it would take to sequence the genome, and they made it on time because computer power increased and technology made the next generation of technology better and so on. My impression was that now sequencing a genome is really fast.
We're a lot faster than we used to be. The other thing that got us over the finish line in 2000 was that there were actually two different teams working on it, sort of the official team and the other team. And the other team was using some faster technology, and together they managed to make it according to the, somewhat artificial deadline. But we are a lot better at sequencing now. I don't know enough to be able to tell you what the complexities are. I mean, I remember being astounded that the SARS-CoV-2 genome, the virus that causes COVID-19, they sequenced that in January of 2020, which was pretty darn amazing. And that was what led to the mRNA vaccines, which is what I got, probably what most people have gotten. But yeah, so we were able to, and when I say we, I mean greater collective humanity, was able to sequence that viral genome very fast. And that's also how we are able to trace the variants around the world because we can even sequence the various different ones. In fact, it would be nice if we were doing more of that so that we could see where variants start and where they go and all of that kind of thing. So we're a lot faster at it than we were. But, you know, it's still a fair amount of work for something big and complicated. And obviously, where you have a large population, as we do with people, there's going to be variation as well.
So we're back online, friends. So anytime you want to transition back to Ivan's talk, you can finish your thoughts, and then we'll go back to Ivan.
Okay. Yeah. So I'm going to be talking about wave-particle duality. I'm going to explain what it is and give you some insight into what the problem is and how this has inspired different interpretations of quantum mechanics. And with the caveat that there is no consensus on interpretation, although most people that have a preferred interpretation think there should be a consensus around their own. And so satisfaction is not guaranteed in the sense that most people find something unsatisfactory about all of the interpretations, so or all but one. So wave-particle duality, what's it all about? Well, first of all, let's talk about what is a wave and what is a particle. So when we think about waves, we're thinking about something which is usually continuous. It's spread out over space and maybe can move in multiple directions at once. And you can think about, you know, as a droplet of water falls into a pool, and the ringed waves of that collision like spread out in a pond. That's one example of a wave. Waves can also interfere with each other. So if you have two drops that fall into the pond at the same time, as those rings intersect with each other, you'll get reinforcements and cancellations. So you get, you know, the sum of two waves, and sometimes the wave will cancel, the two waves will cancel each other out, leaving a surface that's approximately flat. Particles, on the other hand, have a small size and usually have a definite position. And most of the particles that we deal with in human scale things like golf balls, not only do they have a small size and a definite position, but when they move, they retain those things. So as the golf ball is flying through the air, you don't like lose track of the golf ball. You can see the particle as it's moving towards, you hope, the hole that you're trying to shoot for. But particle properties are usually associated with a small size or a definite position. So wave-particle duality refers to the fact that both light and matter exhibit the properties of both waves and particles. So the experiment that is most commonly referred to when people talk about wave-particle duality is the double slit experiment. So imagine this is a cross-section, and the blue here is a metal plate, and there are two holes in it, or two slits in it. And if you imagine that we have this beam of particles that's headed toward the metal plate, some of the particles will go through the holes and some will just bounce off. And intuitively, you know, if this beam was like bullets from a machine gun, some of the bullets would bounce off of the plate, and some of them would go through the slits, and they'd hit the screen on the other side, so you could see where the bullets landed. And these would typically go through in roughly a straight line. Maybe they'll graze the edge of these slits here and spread out a little bit. But this is what you expect intuitively, and this is the kind of thing we see when, for example, we shoot a machine gun at some windows, and it goes through the window and hits the screen on the other side. Now, when we do the same thing with waves, we'll get a different effect. And this experiment was first done with light by Thomas Young in 1801. And if the wavelength of light is close to the distance between these slits here, then when the wave emerges from on the other side of the slits, you get these concentric rings, which will remind you of that first photo of water waves, like two drops in the same pond where the waves interfere with each other. And where the waves cross, there's reinforcement, and between them, they cancel each other out. And so I put dots over where they reinforce. You can see that this beam now has like spreads out in multiple directions. And the number of, you'll actually get many of these lines in this pattern here that would be projected on the screen. How many you get and how many you see depends on the distance between the screen and the slits and so on. But, and this was taken by Thomas Young to show that light is a wave. And this is compelling evidence that light is a wave, right? In 1927, this same experiment was done with electrons. So electrons are particles. So you might expect that the electron will create a pattern on the screen that resembles the pattern on the very first picture I drew, where you'd have the machine gun shooting through the windows and you just get two patches where the electrons land. This screen would be maybe a screen made of phosphorus or something. And when the electron hits it, it jiggles all the atoms around, and then those atoms emit light. So you'll see a little flash wherever the electron lands. So if you have a beam of electrons, you should see two bars corresponding to the two slits. But what you actually see, again, when the distance between these slots is just right, you will see an interference pattern, just like you saw with light. And now you might think, okay, well, this is confusing. Most people will think this is confusing, right? These are particles. Why is there an interference pattern? Maybe it has something to do with the fact that electrons are charged particles. Maybe there's something about sending a beam of electrons where they interact with each other in some way and create this pattern. But what you can do is you can turn down the intensity of the beam so that you fire only one electron through this mechanism every second. And what you'll see is a particle-like interaction with the screen. Maybe you'll get one hit here, then the next electron will hit here, and the next one, the next one. And statistically, you get this interference pattern that shows up. So it seems like electrons have a wave-like property that gives them this interference. And then they have the particle-like property of when they interact with the screen, they behave like particles. And if you have, a high intensity beam, you see what you see is all these little flashes on the screen. They accumulate in this way. And I got these, some of the article on Wikipedia for this has some really nice graphics and explanation. So earlier on, 1801, there was, we had all this evidence that light was a wave. Well, in 1887, the photoelectric effect was discovered, where you could shine a light on a metal or semi-metal plate, and the light can eject electrons from the material. And of course, this makes sense that if the electrons are held in here by the electromagnetic force, and that if you give them enough energy, then they can escape. Well, there are a couple of ways that you can increase the amount of energy in a beam of light. One is to have a higher brightness, and the other is to change the frequency or the color. And you may know that everything from radio through infrared, visible, ultraviolet, X-rays, and gamma rays, they're all light. It's the electromagnetic spectrum. And this is going from lowest frequency to highest. So at the bottom of the visible spectrum is red, and at the top is violet. So you would think that doing either of these things, either increasing, if light is a continuous wave, then doing either of these things to increase the energy of the light should be able to free electrons. But that's not what happened. It turns out that you need higher frequency of light, that that just raising the intensity of the light is not enough. And Einstein wrote a paper in 1905 in which he showed that the best way of explaining this is if when light interacts in this very particular position in the material, that it works as if light is a particle, and the particles have an energy of Planck's constant times the frequency. So it is as if when the light is hitting the surface and you're looking at this interaction, light is behaving like a particle also. So both light and matter are both behaving both like waves and particles. So it's true for light and matter. And we have to ask, what's going on? Well, in quantum mechanics, propagation, the traveling of, when you have propagation of a field, it is wave-like. But if you have a short-range interaction, then it's localized because it's short range. So it becomes particle-like. So, if you have waves which are traveling and radiating things, while particles are localized and interacting things, there's really no contradiction. There's no direct contradiction between these two things, but it's still puzzling because it doesn't work like all the intuitive things that we know, where things are either waves or particles all the time. So to what I just said, like if it's if something is traveling and it's like a wave, it's not localized, then it's not particle-like. If I try to measure if I put something into this slit here to see if anything is going through, and I get a short-range interaction with this field as it's going through, then what I'm doing is I'm forcing myself to measure the particle-like properties of whatever I'm looking at. But it's still puzzling, right? Because what does it mean? If the wave is everywhere, then why do we observe the electron in only one place? Like, what's the rest of this wave for, right? Like, what does that mean? Well, there are a couple of interpretations that I'm going to talk about. And one of them is the pilot wave interpretation. And in this interpretation, particles are like balls that are riding on these waves. And where the waves destructively interfere, in other words, where the total goes to zero, then you won't find the particle there. But where the waves constructively interfere, you're more likely to find the particle. So, for example, in the center here, where you get this constructive interference, then you're more likely to find the particle here. But where there's destructive interference, you won't find a particle at all. So the advantage of this interpretation is that we get to keep our intuitive notion of what a particle is, right? Like, just like in physics, physics 101 or physics in high school, particle is just a billiard ball. Maybe it's incompressible, maybe it has a charge or something. And what it's doing is it's just riding these invisible waves, right? The way we make the waves visible is by looking at the way they carry stuff around. The disadvantage of this picture is that it violates relativity, because when you want to say, okay, well, quantum mechanics tells me how to calculate what these wave patterns look like. So when I go to do that calculation, in order to do this calculation, these waves depend on the position of all the matter and energy in the universe at this time. But in relativity, there's no such thing as this time everywhere, right? It's in this theory, the value of these quantum waves, which are carrying the particle at this point in time, depends on what's going on in my lab experiment and what's going on right now in the Andromeda galaxy, which means there'd be a signal faster than light, which is affecting this wave. And of course, that's why it seems random to us, because it's too hard to predict, right? But it's most people that are rejecting this idea are doing it because this seems to be violating relativity in a particularly offensive fashion. So another interpretation is to say that it's just pure waves. Then this is the basis of the many worlds interpretation. And the idea is that it's waves all the way down, and the wave has short-range particle-like interaction in all the possible places on the screen. So it's not, we're not singling out one place and saying, oh, the electron landed here. The wave actually, these waves scatter off of everything. But the consequences of this interaction here, when the wave scatters from here, those consequences cannot interfere constructively with the others. And you can do this calculation, and you'll find that as long as this screen contains enough interacting particles, that the probability that they'll interfere constructively after this point is effectively zero. Now, of course, we the human observers, when we're looking at the screen, we're made out of the same stuff as the screen and the particles. We're made of electrons and protons and neutrons and quarks within that and so on. So we're making these observations, and likewise, we're no different from the screen. Once we see the consequences of this wave impacting on the screen here, we become cut off from the parts of us that could measure the alternatives. But in this picture, all of the alternatives actually exist. So the wave is, in the many worlds interpretation, the wave just continues. It hits everywhere and it scatters off of everything. It's just that the different parts of the wave can, when you get an interaction which is statistically irreversible, they will no longer interfere. And so those parts of the wave can no longer interact with each other. Now, there are numerous interpretations of quantum mechanics. And again, Wikipedia has some nice summaries of the different interpretations. Most people don't like the many worlds interpretation because they think that, well, what about all these unobserved worlds? I don't see other versions of myself measuring the other outcomes. So this seems problematic. But there are some nice advantages. One of them is that all the other interpretations also contain waves all the way down as well. So for example, the Copenhagen Interpretation, which has wave function collapse. If there was no collapse, it would just be the many worlds interpretation. So they all have, all these other interpretations have many worlds in them. In the pilot wave theory, if you ask like, well, okay, so I have this particle that's riding the wave. What does the particle actually do? Well, the only thing it does is it just picks out our one world as you are here. But in terms of predictions, it's no different from many worlds. The other nice thing about many worlds is that it's consistent with relativity, but it's not the only interpretation that is consistent with relativity. It's really the pilot wave is the one that's the most disturbing. And so I hope after this presentation, you know what I mean, what we mean when we say wave-particle duality. And I hope that these interpretations give you some intuitive feel for what's going on. Like you may have heard that in quantum theory, there's one school of thought which is shut up and calculate. So in other words, don't even try to interpret it, just do the calculations so that you know what's going to happen. But the reason I find many worlds so appealing is that if all the other interpretations have many worlds in it, what they're doing is they're just adding extra physics to try and say, hey, I don't want to think about those other worlds, so I'm just going to do something to say I don't want to think about it. But many worlds is simpler in the sense that if you don't make any other additional assumptions, it already explains all the phenomena that we see. I was going to talk about Fourier transforms and breaking waves down and so on, but that was getting way out there. So I hope I've done an adequate job of explaining this without any mathematics.
Yeah, that was great, Ivan. Thank you. So a couple of thoughts come to mind immediately. One is that a lot of times there's this notion that seems somewhat widespread in the general populace that quantum mechanics is not what's called deterministic, right? That if you know the past, there's no way to predict the future. And because of that, anything is possible. You know, the infinite worlds open up, and just by wishful thinking or, you know, doing the right ritual or whatever, you can make anything happen, because in quantum mechanics, literally anything goes. And one of the things that when I've given some science talks about quantum mechanics that I've tried to stress is that the mathematics that describes everything you just talked about, the mathematics is completely deterministic. The mathematics is clear, and it tells you about probabilities of different outcomes, but the mathematics is not ambiguous. The mathematics is as information rich and complete about describing the system as Newtonian mathematics. Is that an accurate point of view, do you think?
So there's deterministic, and then there's predictable, right? So in the Copenhagen interpretation, what happens is when you make a measurement, you force the wave function to collapse into a state corresponding to what you observed. It's like when you make an observation, you just throw away the rest of the waves and say, oh no, it's the wave. It's actually what corresponds to what we observed, and you throw away the rest. And there's this notion of collapse. So that instead of being a superposition of different possible things, now it's just the one thing you observed.
Like, oh, well, the others were just not right.
Well,
right.
Can I chip in here?
Yeah.
So first, I think it is not deterministic. I mean, because it gives probabilities of different things happening. By the wave propagation obeys Schrodinger's equation is deterministic. But where the particle appears, for example, on your screen, is given by a probability. It's not determined ab initio. And so you can have an arrangement where if it hits one part of the screen, it'll blow up an atom bomb. If it hits the other part, it won't. So the probability is not at all determined like that. And about observation, about the Copenhagen interpretation, which I think is very flawed actually, because they talk about observation or measurement, but they don't define what they mean by observation.
Right.
So, and people bring in consciousness, and the consciousness observer collapses the wave function when it enters the consciousness, which is ridiculous in my opinion, because, you know, certainly the first billions of years of the universe, there were no conscious observers to collapse anything. Now, so as Ivan rightly said at the beginning, you know, there's so many different views, people disagree about views and so on. In my opinion, and this is, I believe that the observation can actually be tied to a jump in entropy, which is a well-defined thing. So, okay, and John's raising his hand. So for example, when a particle goes through a bubble chamber, okay, it's going through the bubble chamber, and along the path, it ionizes an atom, and that can cause a bubble to form. Now, when the ionization occurs, the entropy of the system jumps because there are so many possible ways in which the atom can be ionized. The electron can jump out in all sorts of directions. So the entropy jumps, and that, in my view, is when the wave function collapses. And then it continues as a wave until it ionizes another atom. So in the Schrodinger's cat story, which has got so much, books written about it, I think it's ridiculous to think that the cat is in a superposition of alive and dead states until a conscious observer opens the box and looks in. So what happens in my view, and I think it's a perfectly realistic view, is that when you have this radioactive isotope that's got a 50-50 chance of emitting an alpha particle or whatever.
A cat killing bullet.
So, when that particle clicks the Geiger counter, which breaks the vial of cyanide, it's when the particle clicks the Geiger counter, that is the event when the entropy jumps, because the Geiger counter is triggered by an ionization occurring. So I identify observation with jump in entropy, which is when the system goes from a low number of states to a high number of states. That's, and I could go on talking about that. That's my view. The many worlds I don't like either, because you say it's consistent with relativity. Ivan, I don't understand that, because, well, for one thing, I think that relativity, as done by Einstein, forbids matter particles from traveling at much faster than the speed of light. But that's a matter particle, or particle with energy. Wave function collapse will happen fast speed of light. Nothing material is moving. Now, this is mysterious, okay. But I think relativity forbids any particles with mass or mass energy from traveling faster than the speed of light. But we see in these experiments on Bell's paradox and so on, that influences or something, the wave function collapses faster than the speed of light. But nothing material is moving. This is a mystery thing, but I don't think it violates relativity, because nothing material is moving faster than the speed of light. I should stop. Okay.
Well, let me talk about an actual application of some subtle quantum mechanics. My friends at who work on the LIGO experiment, that's the gravitational wave detector, they use these incredibly precise optical interferometers using lasers. And their measurement precision is limited by the phase fluctuations in the laser light, which are predicted by quantum mechanics. But they adopt the model that those fluctuations are actually due to vacuum fluctuations of the electromagnetic field propagating into the laser through the beam dump port. And that turns out to be quantitatively right. You can, if you're familiar with the stimulated emission idea, stimulated emission can be successfully modeled as, I'm sorry, the spontaneous emission can be successfully modeled as stimulated emission due to vacuum fluctuations. Now, there's an interesting thing about vacuum fluctuations. You can adjust them with active optics. And so what they do is they actually do something that's called squeezing the vacuum. And that they present that squeezed vacuum, which has greater amplitude fluctuations and lower phase fluctuations than random, to the output port of the interferometer. And they see lower phase fluctuations in the interferometer, and they get more instrument sensitivity. So what is happening is the randomness that is apparent in the laser is due to influences coming from the rest of the universe. And by adjusting those influences, you can adjust the nature of the randomness. Now, I don't know how that relates to what Ivan is saying. I am an experimenter. I am much less interested in interpretation than in give me a calculation and let me see whether it works.
Well, I do want to say something about what you said, Mike, about entropy, like the increases in entropy. Well, that is how it works, right? Like when it comes to decoherence, when you have something which is essentially statistically irreversible, which is just like when you have a chamber where all the gas atoms are start out in one corner, right? After a while, the gas spreads out, fills the whole chamber, and it's still possible. It's still at a fundamental level, it's reversible. So there could be some date in the future in which all those molecules just happen to bounce into that corner again. But the probability of that happening is so low that
Really low.
you just treat it as a bulk material, right? So it's there's this very strong parallel, so that when you have a coherent state and it decoheres, it interacts with an environment where it can spread the energy and the quantum numbers around, that is very unlikely to interfere. We're very unlikely to observe an interference between that and something else. But the issue, like in the many worlds interpretation, what happens inside the box is that now you have decoherence, that the cat is alive. There is an alive cat and a dead cat. And when you open it, you split into observes alive and observes dead. And in each case, there's decoherence occurring. It's just that, and this would have to happen, right? If you expanded your experiment, instead of being, Schrodinger's cat, it's going to be Schrodinger's cat plus observer in a box.
Mm.
Right? And you do the count, like we're all quantum systems.
No, but keep consciousness out of it. I mean, what about Schrodinger's mouse? You put a mouse instead of a cat, or you put a cat and a mouse both in there, Is the mouse conscious? Does it observe whether the cat is alive or dead?
Right. Consciousness has nothing to do with it. You say, it's decoherence. Decoherence is anything statistically irreversible. So when that electron hits the screen in the double slit experiment and hits all those atoms and jostles them around, that's statistically irreversible.
Yeah.
You cannot make a container that excludes vacuum fluctuations in the gravitational field from the cat. And so the cat is constantly being juggled by vacuum fluctuations. And the cat is a very complicated system, and it is always incoherent.
Oh, come on, John. The quantum fluctuations in the vacuum from gravity are so minuscule compared with any fluctuations in electromagnetic fields, for example, that exist there too, that they just have no effect.
Well, you can talk about the possibility of making a really good electromagnetic shield, but maybe you cannot possibly make one good enough for the experiment.
Perfect, as it were.
Yes.
Yeah.
In any case, the box is not perfect. The box cannot be perfect.
Yeah.
And therefore, the cat is subject to fluctuate. It is subject to influences from outside and must be a decoherent system. I mean, a consequence of the LIGO stuff is that the whole universe is deterministic, but the laser is not deterministic because the news of what's going on in the vacuum out there hasn't arrived here yet.
Well,
To answer your question, Scott, about determinism, different interpretations are either deterministic or not. So the Copenhagen interpretation is not deterministic in that the randomness is like ontologically real.
Okay.
Right. That it's impossible to say what the outcome is. The many worlds interpretation is deterministic, but it's not predictable from our perspective to know which part of our wave function we're going to be when we make the observation.
Yeah. Well, and not all, and we aren't continuous, right? As I understand it, according to the many worlds interpretation, it's not just that the electron sort of fractures into all possible states, but so do you. and I and everybody else. So the universe, if you look at it as a giant wave function that constitutes all electrons and protons and neutrons, etc., including the ones in us, then the universe just moves ahead as a wave function. And where we as conscious beings find ourselves is not in any way determined by some preferred location. It's just our consciousness is necessarily continuous, and we happen to exist as part of a continuum of potential consciousnesses, and we can never interact with the other parts of the wave that we're not writing, you know.
Is it useful to talk about the wave function of a cat? I mean, you'd have to talk about something. The cat has got, you know, you need like 10 to the 28 dimensional space to describe the wave function. It's a huge number of dimensions because all the atoms, electrons in the cat have got their own position and momentum. For every particle, there's six dimensions, right? Position and momentum. It doesn't make any sense. It's useless. Okay. So I think that, you know, you can talk about the wave function of a neutron, or even after the neutron decays to a proton, electron, and neutrino. Now, thought experiment. I've got a neutron sitting there in the middle of a vacuum tank that is a large sphere around the neutron. The neutron's got a half-life of, let's say, 15 minutes. So in 15 minutes, half of them may have decayed and half of them may not. I don't know, can't predict that. But once it's decayed, there are so many possible ways it can decay in phase space with the electron, neutrino, and proton going in different directions. That is a huge jump in the number of states the system has. And the log of the number of states is the entropy. So the neutron decays, the entropy jumps. Okay. Now, nobody knows about that until the electron or the proton hit the walls of the tank and cause an interaction when the entropy jumps again. And then the thing, you know, so, and it collapses and collapses and collapses. As I first heard about the many worlds interpretation, it was saying, well, in the double slit experiment, the electron goes through both slits. But when it does so, the universe splits into two copies of itself. One, the electron went through slit A, the other electron through slit B. Now that's ridiculous for the universe to split in two, because most things are not either or, one slit or the other. You know, a particle scatters on another particle, and there's a vast number of possible final states, you know, millions of final states depending. Now the universe doesn't split in a million different ways. Every particle interacts. I mean, it doesn't make any sense to me. It just seems crazy. So, I mean,
so when you want to sell me an interpretation of quantum mechanics, you have to tell me an experiment I can do.
That you can select between them.
Yeah.
So
Well,
physics is an experimental science. This is not mathematics.
right.
So I do want to address that, because a lot of people, when they think of the many worlds, they think that the universe is splitting, as if we're going to make a completely new copy of everything in the universe, right, so that, you know, we'll never end up with one outcome interacting with the other, right? That's not what it says. What many worlds just says, just talk about wave functions only, period. Just use Schrodinger equation, do your wave functions, calculate your cross sections, whatever, and that's all you do.
Even for the cat.
Right. And then you just say, you know, in other words, take into account that observational devices, that we humans as observers, we all have wave functions. What would happen if, you know, the electron goes through, you have a wave function corresponding to the electron, it goes through the double slit, it hits the screen, shakes up the atoms in, you know, the wave function, there's components of that wave function, right? There's an overlap between the wave function of the electron going through the screen and the atoms, and that there's an overlap wherever that interference you know, pattern is non-zero. There's an overlap there. So then you can say, okay, well, so then what is the probability that that part of the wave function carries through to the observer and so on? If you do that and then say, okay, that tells me the probability, that gives me the correct pattern. And then you say, okay, but then what is the probability that this observer who saw the electron land here can somehow see interference with the electron landing in another place. They cannot.
Yeah.
So wave mechanics by itself, Schrodinger equation, nothing else. In other words, you take everything that every theory of quantum mechanics already has, you get exactly the same result as many worlds. Hilbert space already has infinite dimensions, so 10 to the 28 is no big deal.
So Ivan, here's a question to you about if you're just thinking of a wave. Now the electron has an electric charge, okay? Two electrons, both with electric charge, they repel each other, and I can calculate that. Now, if I just think of waves, where is the electric charge of the wave? And for John's answer, can I do an experiment to determine that by having the two electron waves, one for each electron, and trying to find out where the electric charge is located? I think if I do that, they collapse to particles, but I don't, it's a thought experiment. I don't know if anybody's can try to do that. Where's the charge located in a wave?
So
well, if you just take, Schrodinger's original model of the hydrogen atom, the energy comes from assuming that the charge is spread out according to the square of the amplitude of the wave function.
So that you can calculate the force between two electron waves because they've each got a charge. It's spread out, and I integrate over.
Well, again, I'm talking about the energy, not the force.
I'm talking about force.
But you get the
where the charge is located.
You get that if you stick a proton and you stick an electron in the in the 1s orbital, and you calculate how much binding energy you have for that electron attracted to that proton, classically now. Okay, now it gets more complicated. You want to do it relativistically, but if you do it classically, this is Schrodinger's original model. What you get is you get the right answer if the way you write the Hamiltonian is that the energy is the integral over the all the places that the electron could be, and the electrostatic potential of the electron at those places.
So it is smeared. Yeah.
Yeah, it's a smear.
Yeah, so localization has to do with the experiment that you do that has a short range interaction, right? So let's say I locate the electron by shining a photon at it, right? And I have this short range interaction, and if the wavelength of light is too big, then I don't really know where the electron is, right? I have to make the wavelength small enough, and then it becomes a higher energy interaction.
And then the photon interacts with the electron, and that is, when it does so, the entropy jumps because there's so many ways the final state can be.
Yeah.
Right. Now, by the way, I've done this experiment at Fermilab of colliding two photons and making electron-positron pair or a mu plus mu minus pair from gamma-gamma collisions. We did that in the Tevatron, actually.
Right, but you can easily, though, still create an interference pattern. If you have a small enough number of particles, yes, there is an increase in entropy, but you can still then, put some mirrors up and get recover an interference pattern.
But let's look at, for example, what happens when we do a transmission grating experiment with the Chandra Observatory. You're looking at an astrophysical source of X-rays, and they come in and they go through the slits in the grating. This is more than a 2-slit experiment. This is a lot of slit experiments, but it's basically the same thing. And they interfere like waves. Now, what's happening is because of the construction of the machine, the internal degrees of freedom in the grating are really well isolated from the electromagnetic field. And so you get this coherent behavior. There's no incoherence in the interaction between the electromagnetic field and this grating. And the direction that the exiting radiation goes depends on the wavelength. Now they hit my detectors. My detectors are silicon crystals. I have no idea how to make a quantum model of a complete silicon crystal. It has all those darn degrees of freedom, and they're not at zero temperature, and it's very complicated. And so the interaction of the X-ray with the silicon crystal, well, you can kind of get it a little bit by thinking about how a wave interacts with an electron that's bound to an atom. You know, it wiggles the electron and yada, yada, yada. It's quite probabilistic, and what you really see is energy deposition by photons, because you can't really treat the silicon crystal as a quantum system. It's too complicated. It has too many degrees of freedom. You cannot tell what's going on in those degrees of freedom. And it works.
It's much simpler than a cat.
How it works.
It works.
We can design instruments using this, and we can point them at the sky, and we can figure out what's going on in distant galaxies and all that.
Yeah, John, when your electron scatters from the crystal, it doesn't do so.
It's a photon.
Photon.
Well, the photon is coming in through the grating.
Yeah.
And it scatters off in a direction that depends on interference.
Right. So
now the photon hits the crystal, and there's a photoelectric interaction. It's that old photoelectric effect.
Yeah.
And so you get a hot electron, and now that electron is very complicated. It bashes into more atoms and makes more electrons. And in the end, I measure how many electrons it made, and that tells me, how much energy that photon has. And that's good, because the direction that it went off the grating is a bit ambiguous, because there are multiple spectral orders, and so waves of different wavelengths can wind up in the same place on the detector. But we can tell which order we're looking at by using the coarser energy resolution of just measuring the energy, using the coarser resolution of just measuring the energy by how many electrons it made.
So one of the things that occurs to me is that the mathematics between all these different interpretations of quantum mechanics, the mathematics is the same. You know, the Copenhagen interpretation has this mystical wave function collapse, which doesn't show up in the equations. The pilot wave presumes that there is a wave that particles ride, but there's no distinguishing particle wave separateness in the equations, as far as I know. So this is all about interpreting the math, which itself is very consistent. It just tells us something about reality that we have a lot of trouble thinking about. And, many physicists throughout time have said nature is under no obligation to make sense to us. I mean, look at the platypus, right? There are all kinds of ways that nature can exhibit properties and entities that perhaps just don't make sense to us, because we're used to living in a world of baseballs and ocean waves, and not in a universe of particles that have an indistinct boundary, and that travel. Even the solar system idea of the atom. You've all seen in textbooks this idea of a little nucleus, and the electron spins around the nucleus like a planet. Right there. Yeah, and you can see it in the picture. Well, that's nothing at all.
And we still call the wave functions orbitals.
Right. Yeah. Right. The orbit.
As you just said, the S1 orbital.
Right.
Yeah, I did.
I never knew what he meant.
I don't know what I meant.
Yeah.
But Ivan, what we haven't mentioned yet is Bell's inequalities, right? So this was John Bell was at CERN. I sort of knew him a bit, and very great theorist. And he proposed a test to see whether the wave function collapse was local or not local, in a following sense. One way of describing this is the following. You can take a particle with a neutral pi meson. It's a pi meson, and it decays to two photons, two gamma rays that shoot off in opposite directions. Now, the spin of the pi zero is zero, is nothing. It's got no spin, but the photons themselves have got a spin. So for conservation of angular momentum, the two photons must have equal and opposite spin. Right. Now, but you don't know what they are. And you can go a kilometer away in each direction to try and detect these photons. And when you detect one photon, the other one has to have the opposite spin. Now, you can vary the orientation of your polarimeter, if you like, or spin detector, on photon 1. And as you do so, photon 2 knows it's got to be opposite. And yet they're a kilometer apart and they're interacting within a nanosecond of each other, whatever. See? So Bell said, is this really true or not? And he made and it's a probabilistic thing, but he made an equation. And if the result of this correlation was negative or positive, I forget which one, he showed that it was actually, there was no communication between them. It had to be somehow the wave function collapsed faster than the speed of light. Okay, so, and I think we should just have to get used to the fact that wave function collapse is a real thing, and it does happen faster than the speed of light, and it doesn't violate relativity because wave functions, you know, it's mysterious, but they don't have a mass. You're not sending something with mass or energy faster than the speed of light. But even if you do,
you say you knew him. I've read that he expected that when this was tested experimentally, the wave function collapse would fail.
Yeah.
And of course it didn't.
I did know him because I was at CERN together. Actually, we were on the same committee together. Here's a story, an anecdote, if you like. There was a famous book written by a guy called Gary Taubes called Nobel Dreams. And it was all about Carl Rubbia dreaming of the Nobel Prize when he was going to discover the W Z bosons. I was on that project, actually. So, and this book was not very complimentary or flattering to Carl Rubbia. And it appeared in the CERN library, and then it disappeared. Carl Rubbia wasn't director yet, but he had a lot of influence. And John Bell and I were on the library committee, and we were able to get it put back in the library because he said, we can't censorship like that. But anyway, that's my brush with the fame.
Regarding Bell's inequality in the experiment, it shows that, you know, if collapse occurs, that it happens faster than light.
Yeah.
Right. It doesn't violate relativity in the sense that you can't use it to communicate faster than light.
Yes.
You know, the actual, you know, physics that it predicts is still compatible with relativity, but it's as if there's a superluminal communication between one measurement and the other, right? But that doesn't mean to say that there is collapse, right? Because you get the same result in many worlds without any collapse.
Joanne, you have a statement to make, I think.
No, actually, the man up
You had an obligation to make sense.
I like that shirt. Yes, that's something I would get for myself. That's very nice.
completely apropos to this discussion. I love it. Dave just came from downstairs and upstairs and brought it down. Going, here, show them. This is perfect.
So I think we're at the end of today's time. You know, at the very least, I hope we have helped add some clarity to this this perennial debate among physicists and philosophers about wave particle duality. But the underlying reality of wave particle duality is not something we can argue with. Sometimes
I find it most interesting that here we are discussing this and we're going back and forth, and I'm looking at our computers and our devices here, and light is coming up here, and we have stuff going on there, and with electrons going around all over the place, and we're discussing, could it possibly exist?
Maybe we're just each other's imagination. You know, remember there's this famous idea. I don't know if it's apocryphal or if it really occurred, but that Einstein was walking along some avenue with Niels Bohr, and Einstein said, "Do you really think that the moon does not exist if nobody observes it?" And I'm paraphrasing, I think, but and it was said in German, but.
So it made much more sense.
Right, yeah. But I believe that according to Bohr, you know, if he stuck with strict Copenhagen interpretation, he was obliged to say, no, the moon does not exist until you observe it. And then in the nearly 100 years since then, we've refined some of the philosophical interpretations with this notion of, like Ivan was saying, decoherence, and looking more carefully at what wave propagation implies. But it's an ongoing debate. We're probably not going to solve it today, but hopefully you've gotten a sense of both the debate and the relationship between waves and particles. So
before we finish, there's another Bohr story you remind us of, which you probably know, but I think it's Heisenberg visiting Bohr in his summer cottage. And there was a horseshoe above the door. You know, horseshoes to bring you luck. And Heisenberg said, you don't really believe that brings you luck, do you, Bohr? And Bohr said, no, I don't believe it, but I'm told it works even if you don't believe it.
Excellent, excellent note.
Physics.
Yeah. Excellent note to end on. So thank you all for tuning in. Apologies for the technical problems. I'll try to go in retroactively and edit these videos, splice them together as one for publication on YouTube. And we'll be back in a couple of weeks to talk about another science topic. So
Thank you, Ivan. Wonderful discussion.
see you
Great
all
to see
soon.
you
Yeah,
All
thanks very much.
Thank you.
This is fun.
right, bye-bye.